the language of the universe.
But I don't understand it.
Hello, everybody. Welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you back to episode 33, this time, of the Math and Physics Podcast, where today we're going to be talking about something that is insane. I mean, I say this almost every episode, but today we're going to be talking about the Big Bang Theory.
It is probably the most insane thing that's ever happened in the history of the universe.
Yeah, for sure. I agree with that.
Well, I guess, what is the Big Bang?
I guess we can
first
simply
question.
start with it. Okay, so let's just start into the podcast. No quick preamble of the downloads. Quick update, though. We did reach 15K. So, once again, thank you to everyone who's continuing to download and follow our content.
Yeah, also 1,100 followers on Spotify, so that's dope.
That is dope. Once again, thank you to everyone.
Yeah,
okay,
thank
so
you to
let's
everyone
get
that's
straight
listening.
into it. Who theorized the Big Bang? How did the Big Bang even come up? Sorry?
Before that, I'm gonna assume everyone knows what it is, but let's pretend like there's one listener out there that does not know what the Big Bang is.
Okay.
Basically, life as we know it has not always been a thing, right? Mm-hmm. There's a finite amount of time that you can go into the past where everything was just one. Everything was literally in one point with no dimensions ever.
Yep.
And no time, no anything.
Nothing existed. Absolutely
and
nothing.
So it was theorized that, before anything ever existed, there was just like an infinite density, infinite temperature singularity point that just exploded, and then the universe expanded.
Expanded.
Yeah. It wasn't an explosion. It was just an expansion.
That's the common misconception, actually, that we're going to be coming into today. We're going to be basically covering a lot of the points, I think, of the Big Bang, and why it could be the most possible theory to predict how our universe began. Right, so hopefully you guys understood the basic idea behind the Big Bang, just a small something point-like particle expanding into what we know today, right? But
I bet you a lot of people have really common questions that we're going to answer today, and that is, well, how do we know the age of the universe? Like, we have this number that we throw around all the time, but how do we actually know that? And also, how do we know that the universe wasn't just, some big space as we know it today forever? Like, how do we know it wasn't just like this forever? And we'll answer those questions as we go on with the podcast.
So, in around sometime in the years of 1927 to 1932, the timeline is a little bit skewed because no one really knows the exact year. But the scientist known by the name of George Lemaitre, a very, very, very popular scientist, he had a theory. He saw that galaxies, he was actually the first person to discover that galaxies are moving away from one another. Hubble actually did it after George Lemaitre. So the common Hubble law that we know today, the fact that galaxies are simply moving apart from each other, today is actually interestingly known as the Hubble-Lemaitre law. Just cool fact. Anyways, so George Lemaitre was the first scientist, or at least known scientist, to discover that galaxies are moving away from one another. And what he called this effect, the idea behind galaxies moving away from one another and therefore must have started at one initial point, he called that the hypothesis of the primeval atom. Now, that's a very hard name to really pronounce in a day-to-day basis. But now this is where the story gets a little bit interesting. Another scientist by the name of Fred Hoyle, who was a popular scientist in the realm of the steady state theory of the universe. The steady state theory is basically, as Parker mentioned, the universe has always existed, is always existing, and will always exist the way it is. That is what Fred Hoyle believed. Funny story. On a radio show, as Fred Hoyle was being asked, what do you think about this other person's theory, the hypothesis of the primeval atom? He states, and this is quote unquote from the radio show, these theories were based on the hypothesis that all matter in the universe was created in one big bang at a particular time in the remote past. Now, why do I mention that? Because this is the first recorded instance of the word Big Bang. And after Fred Hoyle said it in this radio show, it basically became popular. And now everyone knows it as the Big Bang Theory. Even though he was actually rooting against it till the very day he died. The Big Bang Theory is what is known as today, simply because he was trying to say, yeah, the Big Bang is wrong, but this is right. And all media outlets just caught on to the name Big Bang. And here we have it. Even though it does provide an incorrect representation of the universe, because as we both just stated, the Big Bang wasn't really a bang, it wasn't an explosion, it was more of an expansion of the universe.
Mm-hmm. Yeah. And the cause of that initial expansion is theorized, but completely unknown. Completely. Right? We can throw around hypotheses and be like, oh, maybe it was a spark, In reality, there's a good chance that we're never going to know, but it's not always reasonable to say it's impossible that we'll ever know. Because science just becomes better and better and
more advanced.
Yeah, that's right. Like who in the 1700s would have thought about general relativity being a thing, Even though it's true, doesn't mean like it's easy to come about. So
yeah, for sure. I agree.
Yeah. So same deal goes with knowing the cause of the initial expansion. Yeah.
So many people then wonder, well, then how do we know that this Big Bang theory is even right? Right? Like how can we have an idea? The answer is the cosmic microwave background. Now, the cosmic microwave background radiation, what we commonly call today the CMB, is what is actually the very initial amounts of radiation set off from the expanding universe. The moment the universe expanded from that singular one-dimensional particle, or zero-dimensional technically particle, to what we know today, the second that happened, this radiation has been, radiating ever since then, 13.4 billion years ago. Since then, it has been radiating out in all directions of the universe. Now, how do we know this thing exists? Another very, very interesting story. So in 1964, two scientists were like, hey, we want to detect these radio waves that we're going to bounce off of a satellite that is currently orbiting Earth, and we just want to detect them. That was their experiment. Nothing crazy, nothing too fancy. So to do that, to actually see the radio waves, they had to filter out all the possible background noise that they could see, right? Now, the moment they did this was now this is what kind of caught their attention. The moment they removed the background noise, whatever was remaining was 100 times more intense than what they had thought the lack of background noise would be, right? Because if you remove background noise, well, it should just be like a flat line and you're only trying to measure one common, this radar signal. But because of this cosmic microwave background, this radar signal can also be affected by this background, because the background is everywhere in the universe, and no matter where or when you are, you will be able to measure this cosmic microwave background. So this, in 1964, was the first measurable instance of the cosmic microwave background, even though they didn't actually know it, which is pretty cool.
Yeah, correct me if I'm wrong, but I'm pretty sure, so when the universe was at t equals 0, all right, not t equals 0. Past we're gonna talk about epochs in a short while, but at one point photons were freely traveling, right? Because at one point it was too dense for photons to move around. But once photons were able to move around and the universe became non-opaque or whatever, those initial photons were gamma rays, right?
Yes, I believe so. Because it's just highest frequency, right? Like highest measure.
Yeah,
I think so.
Yeah. So this might be wrong, So if you don't believe me, you can do some research. But
For sure.
anyways, it was either, it was a high frequency photons that were being emitted, and because of the redshift, you can actually perform the calculations from that t equals 0 to now. If you perform the redshifting equations of the wavelengths of the photons, you can actually calculate that those initial photons would be in the microwave wavelength today. Oh. And so that's kind of like an analytic perspective on this cosmic cosmic microwave background radiation.
Yep.
Yeah. So, the reason we're not seeing colors in the sky or in space well, I'm guessing, at
it's
one
still not
point
visible light. It's still not enough to be visible.
Yeah, it's not visible, but it's below the visible spectrum.
Yeah.
But, those waves are there, and we were only able to pick those up because randomly these guys performed their little experiment, and they picked it up, and they're like, wait, we can see these microwaves everywhere we look in space. And so, they came to the conclusion that, they stem from the initial stages of the universe.
Yep. And just also a quick reminder that microwaves are some microwaves are kind of redshifted versions of gamma waves, so the frequencies are lower, right? So after these 14 billion years, what Parker was basically trying to convey is that the light stretched out over time, showing that the universe kind of expanded and is still expanding into what we know today.
And based on the actual frequency that they were detecting, that's one way that they estimated the age of the universe.
Okay.
Yeah.
That's cool.
That's right. So, do you have anything else to say about...
Not really. Not much about cosmic microwave background. I think that's basically just a cool fact that I wanted to say, how they first saw real proof of it. But that's, that's basically, we're obviously going to be talking a lot about the CMB in this video because it's basically the Big Bang, right? It's all about the Big Bang, so.
Yeah. So in the early stages of the universe, there are things that I mentioned earlier that are called epochs, all right? And these are just segments of time, okay? And I'll name them in a few seconds, but you'll see that the first few epochs are so incredibly short that making the distinction between these epochs is purely mathematical,
Purely,
if there was
so purely.
Yeah, if there was an observer, obviously the conditions back then wouldn't allow for an observer to be present, but let's say I was able to put my eyes in the Big Bang situation. I would not the universe would be formed before I could even blink an eye, So let's start with the first epoch.
Well, not the universe, but most of the epochs would be over. Most of them would be over by the time you blink.
Yeah, I didn't mean the Earth would be formed, but yeah. So the very first epoch is called the Plank Epoch. Ooh. And get this, okay? I highly doubt you'll be able to imagine how long this epoch is, but it's from 0 seconds to 10 to the negative 43 seconds, all right? So, okay, I guess all I could say is that imagine 1 second, okay? And then divide that second in 43 times, and that's what you'll be left with. So,
it's a very, very small number.
Yeah, so during this epoch, there was, of course, expansion going on, and basically today we know 4 fundamental forces, and every single other force that we know, colloquially, friction and things like that, they all come from these fundamental forces. And so there's electromagnetic force, strong nuclear force, weak nuclear force, and gravitational force. I did say them upside down though, because the strongest one is it goes strong electromagnetic, weak nuclear, and gravitational. What I always love saying this, because people are surprised when they hear that gravity is the weakest force. They're like, wait, how is that possible? When I jump, I don't go into space, so obviously there's a strong force that's keeping me down. But think about this, okay? If you have a balloon and you rub it on your head, right? it'll stay stuck to your head due to the electrostatic forces, right? Mm-hmm. Now, the fact that it stays stuck to your head means that the electrostatic force of just you rubbing that balloon on your head outweighs the gravitational force of the entire Earth pulling on that balloon. Mm-hmm. Okay? So that's just to put it into perspective. Like the entire mass of the Earth, so I don't know why I said Earth, but the Earth is not even strong enough for, like, you know, for example, a tiny little magnet, right, on a piece of metal, or a balloon being rubbed on your head. Like, it's incredibly weak. Mm-hmm. In fact, it's the weakest. So, so now you know. Strong nuclear. Should we get into the 4 fundamental forces, or should we talk about this in another episode?
I think we can talk about the more in depth in another episode, but I think we can just go over the main things that happened in each epoch, because even though it happened in 10 to the negative 43 seconds, a lot of things happened. Quite a lot of things happened in all of these epochs, even though they lasted for literal unconceivable second, unconceivable units of time. Sorry, is what I mean.
For the first epoch, actually not that much happened, right?
Well,
it was just some
the very, very beginning,
right? It was just the universe was expanding. It was incredibly dense, incredibly hot. It was just, as I've heard before, a soup of things.
Oh yeah, I've heard of that before.
Just running around, well, not, just floating around and being crazy.
Extremely dense at this point.
Right, there's an incredible amount of pressure, an incredible amount of thermal energy, kinetic energy. Just everything is just packed down together. So this was, you couldn't see through anything, because the photons weren't even able to. Or no, there weren't even photons at that time.
No, not yet.
Yeah, not even. And
also, but interestingly, in this epoch though, 2 things that did, well, theoretically, again, because we haven't found experimental evidence, but theoretically, 2 very important things that formed were dark matter and dark energy, both of which formed in the Planck Epoch. And the dark energy, as we know today, is what's theorized to be expanding the universe. So we theorize, just like in the Big Bang, in this Planck Epoch, when dark energy was created, the reason the universe kept expanding is because as it expanded, more dark energy was created, and more dark energy would just expanded even more. And this would basically keep happening. And this expansion rate, interestingly enough, was actually a lot faster, or again, theorized, a lot faster than the speed of light. Because again, it's not something that's actually increasing, it's just dark energy that's being created and created and created. And that's giving the effect of the universe expanding. And that all happened in the Planck Epoch, supposedly.
That's right.
I think all of this is supposedly, because I don't think anything is factual. This is all just theoretically, this is what we think.
Yeah, this is our best and most accurate depiction of what actually happened. Just a little disclaimer, there are going to be many, many details that we will be skipping over. Just because, we would have to do a lot of research, and we'd basically just be reciting facts instead of just talking about it. So instead, we're just going to briefly be talking about different topics related to the Big Bang. So what I actually wanted to say about the 4 fundamental forces is that in the very first epoch, these 4 forces were actually unified, and there was just one force. And as we'll see, through every stage, these forces separate into what we know them today. So the first force to separate was the gravitational force. So, and this was in the second stage, which is called... Well, I guess gravity separates in the first, very, very first, in the grand unit. Okay, sorry, continue. Yeah, so after the Planck Epoch, the Grand Unification Epoch, which began at 10 to the negative 43 seconds and ended at 10 to the negative 37 seconds.
Oh, wow. So much time. What? What did they do?
Yeah, pretty much instantly. But yeah, at that stage, the universe was also very hot and very dense. and very small still. I mean, not a lot of time has gone by. So, it's still very dense, very small, very, everything, but it's expanding as we're going on with these
keeps
epochs.
Expanding as the time goes on. Yep.
Yeah, so during this epoch, the gravitational force separated from the other three fundamental forces. And at this point, the universe's temperature started falling. Before, right, the universe was, I think it was like 10 to the 32 degrees Celsius. So once the universe...
Oh, no, wait.
No, it was Celsius, yeah. Oh. I mean, big deal. Plus 300. What was I going to say? Oh, yeah. It was way too hot for particles to be created, but as the universe cooled down, this is when, things started to chillax a little bit and particles were able to form and, subsequently more complex interactions were able to ensue.
Yeah. I don't think we're going to be going over like every single epoch.
No.
I mean, we can just like kind of summarize them, because I think after the grand unification, something really interesting happens where once gravity separates from the unified forces, then we have the strong nuclear separating from what at that time is called the electroweak, where the electromagnetic and the weak are one. But the really cool part about that, I don't know if I've mentioned this before on the podcast. Have I mentioned quark gluon plasma before? Because it's a really cool state of matter. It's basically where like it's so hot that like quarks, which basically make up like our fundamental particles like protons and neutrons, and gluons that hold those particles together. So at this temperature, it's so hot that all this quark and like all these quarks and gluons, they can't bind together to make a particle. So it's basically just one hunk of quarks and gluons, and it's called plasma because it's at extraordinary temperatures, right? So quark gluon plasma is actually a pretty cool state of matter that you can kind of say is separate, but it's kind of like another plasma. So that
lasted
after the grand unification.
Yeah, it also lasted for a total of like 10 to the negative 34 seconds or whatever.
It was very, very short. Very short. Yeah.
So after the Electroweak Epoch, I'm not going to go into super detail.
Yeah. We don't have to go into each. We just have to like just say stuff happens.
So after that, it was the Quark Epoch, which was at 10 to the negative 12. And then the Hadron Epoch, which was at 10 to the negative 6 seconds.
It's just reciting at this point.
Yeah, and then, during every epoch, there's more, new things that are being formed, as well as the universe is getting larger and getting cooler.
Yeah.
After that, the Lepton Epoch, which is actually at 1 second. So we made it to 1 second of the universe being born.
So just imagine that all of what we have just mentioned, like the Planck, the quark, like the grand unification, all of that happened under 1 second.
Yeah, and like, most of it happened.
Crazy just to think about by itself.
Most of that happened under a quadrillion, billion, zillion of a second, right?
Yeah.
Imagine the Hadron Epoch started at 1/1,000,000th of a second. And then the next one was the Lepton Epoch, which was at 1 second. So everything before that happened in literally less than the blink of an eye divided by infinity, right? So finally, we reached the last epoch that lasted a reasonable amount of time, which was the Photon Epoch, which started at 10 seconds of the universe being a thing.
Yep.
All the way until... we finally see light.
Let there be light. And then there it is.
That's right. New things start happening once again. Also, normal matter is mostly hydrogen. Yep. And it's like 75% hydrogen and 25% helium. And
just proton, electron, basically.
So the rest of the free electrons start to scatter light 20 minutes into the universe. Yeah. So
those are basically the ideas behind the epochs. But one very interesting thing that I do want to mention that also happened in one of these, and like, just as the universe was expanding, something very interesting that we don't see today, actually, that some people wonder about. Many people ask the question, why is there so much more matter in the universe than there is antimatter? Because when the universe was created, right, we know that there's this thing called antimatter. So when the universe was created, why wasn't there equal amounts of both? This problem is actually known as Baryon Asymmetry. It's actually a very popular problem in this Big Bang model, where no one, I don't think there is an answer, at least, but I'm pretty sure there isn't, because no one really knows where all the antimatter matter particles went. It's just a mystery, because technically, if you think about it, right, in a perfect universe, there should be 50-50. Like, why would there be so many more matter particles than there are antimatter? Or why couldn't it be the other way around? What tells our universe to only have matter? And no one, or at least I don't think anyone knows yet. So,
That's right. There are a lot of questions to be asked, and there are a lot of clues waiting to be found that are just lying in space. We just need the right eyes to look at the clues and the right brains to analyze them. And maybe one day we will know a lot more than we know today, which is fairly a lot. But
no, I don't think it is. I we know fairly a lot.
There is quite a bit of information we do know.
Like, we don't even, like, we know, like, okay, matter constituents, like, what, 2 to 3% of the universe as of what we know. Rest is dark matter, dark energy, two things that we have no clue about. So,
yeah, but at least we recognize that there's something we don't know, right? We just have to perform the right measurements or whatever.
Yeah, it's gonna be hard, but I think it's possible.
Yeah. So sure. some honorable mentions within the course of the universe is that 200 to 300 million years into the universe, the first stars start to shine.
Wait,
so that's awesome.
1 minute. Before you continue, though, you just started with 200 million.
Yeah.
Like, our listeners might be like, wait, we were like less than a second in 10 seconds, and now we're 200 million?
Okay, well, there's a lot of...
Interestingly enough, no, it's kind of a short segue.
Yeah, go ahead.
The Dark Ages, the cosmic dark age of the universe, lasted for about 200 million years.
Yeah.
So since the first even though there were photons that were scattered, there was no actual thing, because there was no fusion happening, there was no stars that were formed, there was nothing actually happening in the universe. There were just particles flying about everywhere.
Well, there were things happening on the subatomic scale.
Yes, yeah, but like there was
nothing exciting.
Yes. Yeah.
It was pretty much just like a big cloud of gas and other stuff.
You wouldn't really be able to see much if if you were an observer. It would just be like black. Just absolute darkness. Literally nothing for 200 million years. I just think that's pretty funny that all of that happens like within a second, and then 200 million years they have nothing.
Because one of the reasons why it took so long is because gravity is such a weak force. And so if you didn't know this, now you know. But stars are just balls of gas, right? And so if all the gas was spread out in the universe in the early stages, imagine a big cloud of gas. How long would it take for gravity to just bring that cloud of gas together and to form a huge dense ball of burning gas? And how that actually happens, by the way, is that the gas comes together by the force of gravity. And how does it ignite, right? It's mostly due to hydrogen burning, right, for the main sequence stars, which is what we're actually learning right now in our astrophysics course. So yeah, the pressure just becomes so intense in the core that hydrogen, or let's say like two hydrogen atoms, get pushed together very closely and fused together and they make, well, actually it's four hydrogen.
Four. Yeah, I was just gonna say.
Yeah, sorry.
Yeah.
The four hydrogen atoms get pushed together, and they fuse into one helium atom, and also there's a little extra energy, and that is because of the mass difference between four helium and four hydrogen and one helium. And as we know, E equals mc squared, so you can actually calculate the amount of energy that gets released after this fusion process. And so that energy is what powers the sun mostly. Yep. There are other things going on, but for main sequence stars, which are the most popular types of stars, that's what's powering most of their lives.
I have to mention one thing, even though I know I shouldn't, because it's just gonna confuse people. And I know you told me not to mention it, but when you said it, I had to mention it. Okay. So Parker just said, how there's the cloud of gas and how gravity brings it all together. Now, I have to mention this. I'm sorry. In the world today, where we believe in general relativity, which states that gravity isn't really a force, it's just an effect of space-time. So if gravity is not a force in this general relativistic view, then how did all of these stars and all come together? How did galaxies come together, right? The answer is dark matter. So what gravity couldn't do, because remember, in this general relativity view, gravity doesn't exist. So if gravity doesn't exist, how do these things come together? Well, dark matter, what's governing all of these galaxies, all of these solar systems. I mean, there's dark matter in our solar system. So the dark matter that's governing all of these planetary bodies is basically what's responsible for bringing them together. And then due to their force on each other, they cause then the nuclear fusion, and then stars are born and all kinds of good stuff. But yeah, there are two ways to look at it. I just had to give that explanation, and I think it's a really cool explanation.
Yeah, that's right. So as I stated earlier, 200 to 300 million years into the universe, the first stars started to shine. Yep. And only 500 million years later, the first galaxies started to form. As you know, galaxies are just collections of stars rotating about a very, well, quote unquote dense center, relatively dense, if you're comparing to the outer reaches of the galaxies. I don't know if this is right, but you probably know this, right? Does every galaxy have a black hole in the middle?
No, only the large galaxies, such as Andromeda, the Milky Way, have galaxies in the middle. But Messier galaxies, like smaller ones, like some of them obviously do, but some of them, dwarf galaxies, for example, have nothing in the middle. It's just a spiral rotating about a center.
All right, interesting. Yeah. And as you know,
always, yeah.
Or maybe not as you know, but there are hundreds of billions of galaxies in the universe today, and I think hundreds of millions of clusters, and
I mean, no one really knows, to be honest. Like, we're just assuming at this point.
In our observable universe.
Oh, in our observable universe? Yeah, probably hundreds of millions. Yeah, I don't know. No, because see, there are a lot of clusters that make up a local cluster, and a lot of local clusters that make up a globular cluster or a global cluster, something like that. And then that makes a super cluster. And so there are all these stages of galactic clusters. So to say that there are 100 million of one of them doesn't really, there's so many types. Yeah. So there are just a lot of them. I think that's enough.
So I actually did my research.
Oh.
And that research entails a quick Wikipedia search. Oh. But so after galaxies and all that, it's pretty bland. We know that the Earth/solar system came about around 4.5 million years ago from today.
Billion.
Oh yeah, billion, sorry.
Yep.
4.5 billion. And the earliest single-celled organisms on the Earth came 4 billion years ago.
That is crazy.
So if you just put that into perspective, by the time the Earth was formed, and single-celled life was roaming the oceans of our planet, not that much time went by relatively to the rest of the timeline that we just talked about. So yeah, only 0.5 billion years went by between those two events.
So 500 million. Yeah. You can
After that, photosynthesis started happening 3.5.
Are we talking about Earth formation now?
No, I'm just listing off like some important dates.
Okay.
But yeah, so 3.5 billion years ago, photosynthesis. Molecular life started 1.5 billion years ago. And then, humans came about, like 2 million years ago?
Mm-hmm. Oh, I have no idea. I'm just saying.
So, yeah, if you put that all into perspective, humans have been around for literally no time at all.
Yeah, compared to the age of the universe, which, as Parker mentioned, transition by the way, as Parker mentioned, there is a way to do it. And I think you can talk about that again, because like we can go into a little bit behind how do we determine the age of the universe. Because we were, multiple times in this video, we probably said that the universe began, 13, 14 billion years ago. But how do we really know that? Well, there are multiple ways of doing it. And using the cosmic microwave background is, I think, the best one. Mm-hmm. I mean, I think that's the best one. But another way of doing it, interestingly enough, is the mass relationship with a star's luminosity and the time that it exists. Let me explain. The smaller the mass of a star is, like if for example, the sun will last for let's say 10 billion years. Let's just say 10 billion years. A star that's half the mass of the sun will last for 20 billion years. Why? Because it's less massive, and therefore the nuclear fusion that it needs to produce to be intact is a lot less, orders of magnitude less than a star heavier. And therefore a star, 30 times the mass of our sun will burn out in, let's say, a few 100 million years. So what we can do is looking at very low mass stars across the universe in different clusters. For example, now we have, very, very, very powerful telescopes that can tell all these different properties of stars. So if we point at really old galaxies, old clusters, as in moving really far away from us, or big clusters are usually very, very old. So if we look at those clusters and we look at a very low mass star, we can then kind of estimate the range of how old that cluster is. And when we do this for enough clusters, we can kind of get an idea of how old the universe is. So the idea was measure these stars, measure the luminosity of these stars, and try to estimate the time that these stars have been, quote unquote, in this universe for. And the average lifetime, quote unquote, of these stars was about 13 to 14 billion years. So that's why we say today that the universe has existed for about 13.4 was probably from, much better accuracy and getting down the uncertainty and stuff. But this is the basic idea.
Actually, the official value we have is 13.799 plus or minus.
12.4?
No. It's yeah, so 13.799 plus or minus 0.021 billion years.
That's pretty decent. That's not great, but that's pretty decent accuracy.
Yeah.
Like within the range of 2 million years or 20 million years or something?
20 million, yeah.
Yeah, that's not bad. That's
20 million years? That's not bad.
20 million for us is crazy,
yeah.
But for the universe, it's not, because the uncertainty always depends on the measurement. I think the higher the measurement, it's just higher the uncertainty.
And one thing I was so surprised to see is how much astronomers and cosmologists approximate things. In our class, instead of doing we do it to the ability of our knowledge today in astrophysics, right? And the way that we use the information that we have about stars and everything that happens out in space is pretty good, but we find ourselves doing approximations most of the time, right? Because there's no point in trying to account for every little like process that goes on. For example, if you're trying to estimate the lifespan of a star, what you'll do is you'll just focus on one aspect. Like I said, hydrogen burning, right? You can estimate the lifetime of a star based on just how much hydrogen it has and its current luminosity, I believe. Something like that. Anyways. But yeah, you form some accurate approximations, but I'm not, coming from just foundational physics in first year. I'm not really used to just doing approximations instead of actual calculations. Yeah, one thing I definitely want to say before we have to end the episode is when people ask, what happens before the Big Bang? Like, what was going on before the Big Bang? And one thing that I always like to bring up when this question comes up is you can imagine that time before the Big Bang is not defined. It just doesn't exist. And in your head, you're probably thinking about time as linear. And so, after zero, it's just cut off, and that doesn't really make sense. But imagine time as a sphere where the north pole of that sphere is time equals 0. And then as time goes on, the points on the sphere go around and towards the South Pole. And so, for example, if we were along the equator, which is, let's say present time is the equator, and I said, okay, well, look back into the past, you would go towards the North Pole, right? And anywhere you are on this equator, you would head towards the North Pole, right? So you can say, okay, we'll go this far back in time, 10 billion years, 12 billion years, 13 billion years, and you'll get closer and closer to the North Pole. But when you get to 13.8 billion years ago, you are standing on top of the North Pole. So there's no direction you can walk in that will bring you further back in time. Everywhere you go, it'll just bring you somewhere that is closer to today than it is from before the Big Bang, which just doesn't exist, right?
And this is all because, just because we really have no idea how to theorize or even how to begin with what could have been before the universe. Because the way we define our universe is that our universe, as Parker said, let's say, is in time, is the sphere. That's how we defined it. And that's how we will always live in it. We will never, ever be able to know what is on the other side of the sphere. Is there another sphere? Or because there are a lot of theories that suggest that there was a universe before this one that then collapsed and then made this one, for example. And there are many theories, that say that this is the only and will be the only universe that exists. But again, there's no way for us to prove which one is right or wrong. So all we can do right now is stay on this sphere and just live with the fact that we're on it, because we can't do anything about it. We can't even think about what could have been before, because there's no physical way for us to know.
Well, very interesting things for you guys to digest. Very interesting things here. We're going to end the podcast here. This was an awesome episode.
Yep.
Let us know if you want us to do another Big Bang episode. Maybe
for sure.
Big
There
Bang.
are actually other things that we can talk about, like go into depth.
Yeah,
or
that's right.
Let us know. Definitely let us know if you guys want like a standard model of particle physics episode, like as Parker was saying, where we talk about, the 4 different types of forces and stuff like that.
Yeah.
So if you want us to go in depth in that, for sure, tell us. Shoot us an email, DM.
Yeah, so leave a like. Make sure to listen to other episodes of the podcast, because everything we talk about is awesome. Other than that, leave a follow, leave a comment, email us if you have any questions. Instagram at math.physics.podcast. This has been episode number 33 of the Math and Physics Podcast. And I'm your host, Parker.
And I'm Ray, and we will see you soon.
See ya.